Hello everyone, this is the fifth lecture of this week. In the first four lectures, we discussed the truss elements and beam element, and as I said towards at the end of the previous class, in all these formulation you could correlate with the formulation that you studied in matrix method of analysis, because in a way they are very similar. But now today we will see, when we talk about, you see, there is nothing like beam or truss or something in the nature. Every object you see, they are essentially some three-dimensional object. Okay, it has length, width and breadth. But yes, in some cases the one dimension is very large or two dimension is very large compared to the third one, and in those cases we can idealize the structure as beam, as truss, as plates or as shells. So when you talk about truss, beams or plates, they are different kinds of idealization. So two idealization we discussed, one is beam and truss. Now many problems we come across, they cannot be idealized in one dimensional. We need to idealize them as a two dimensional problem, and there are many cases we even cannot idealize a structure as two dimensional. We have to actually deal with the three dimensional problem. So if we have to now today what we see is, if we have those class of problems, then what are the options we have in finite element method, how to discretize them, and what are the different kinds of elements we have, that we are going to see today and in the subsequent classes. Okay, so some example of two dimensional and three dimensional discretization. You see, this is a dam problem which is discretized by a four. Let us not bother about what is the characteristic of the element, but what you can see by looking at these are three dimensional figure. This is a bracket, this is a rotor, this is a some machine tools. Okay, this is a plate with a hole in it. Now what you can look, what is important here, you see is that every element, for when you discretize a three dimensional object, we need a three dimensional elements. All these are all elements. These are all. So when we say this is one element, so this is one element. Okay, this is one element. Similarly, here also this is one element. When you take, this is one element, or this is one element, and then here also this is one. These are different elements. This is, here also we have a different kinds of elements. So what you can make out is these different elements are having different sizes, different shapes. Even in one body we can have, we have for instance, here we have a very smaller elements, but here we have a very large elements. Okay, so the elements are not same in shapes and sizes. Okay, but for different structure we can have different, we need different kinds of elements. Okay, so let us see what are the options we have broadly. So these are different kinds of elements that we can have. For instance, if it is a 1D problem, then then we have two noded element. Two noded, it could be a bar element or it could be a beam element. Both we discussed in the previous classes. We can have three noded element as well, where in a two noded element, every node we had for a beam problem, every node we had 2 degrees of freedom, so total 4 degrees of freedom in an element. But if you have a 3 noded beam element, so total degrees of freedom are 6 degrees of freedom. Why we need 3 noded element or 4 noded element, we will discuss at the end of this week. So these are the things that we have in 1D problem. We have discussed that in the previous classes. Now if you have a 2D problem, then different kinds of 2D elements are, we can have this. We can have a 3 noded element, triangular element. Triangular element, then we have a similar kind of element but 6 noded. We can have a 4 noded element, we can 8 noded element, even we can have several other many other possibilities are there. This is just to give you a rough idea about the different kinds of elements. Even we can have, you can put some more nodes here as well if you want. Okay, so in that case this becomes 16 nodal element. That possibility, that option is also there. So you can formulate such elements. Similarly, if you have a 3D problem, then these are the different kinds of elements that you can have. Okay, now you see, as I just now said, for this you have done the similar exercise in structural analysis, so you could correlate, but these are the things that you have not done before in any structural analysis course, and this we are going to discuss. So, what we do today is we will talk, since it is not the, it is as I said at the beginning of this week, our objective here is not to learn finite element method, because it is anyway not possible in 1 week time. Here is to just see some of the salient features of finite element method, so that you can so that it gives you a sufficient reason to think or to go through the books and learn this subject. What we do here is we will take a 3-noded element and 4-noded element, and then see what is the form of the, what is stiffness matrix for this, and in both the cases. Okay, great. So, let us start this. So, let us start first 3-noded triangular element. Okay. Now, so you see, suppose this is your 3-noded triangle. First, let us take one coordinate axis. So, suppose this is x coordinate and this is y coordinate. Okay. And in this x coordinate, y coordinate, you have an element like this, which has 3 nodes. So, this is 1 node, this is 1, 2 and 3. Okay. Now, this is any representative element. The same thing we took while deriving the stiffness matrix or all the shape functions, we took a representative element for truss and beam, and the same thing we are going to do here. Now, what are the degrees of freedom we have? Now, this is okay. We will come to that, but before that, let us discuss one important thing, that you see, if you recall, you have done it in a solid mechanics course and also in strength of material course. When we talk about two-dimensional problem can have two idealization. One is a plane stress problem and a plane strain problem. Plane stress problem is where your stress stays in a particular direction is 0. So, or it is so small that you can neglect it. Okay. For instance, if you take a paper like this and apply some in-plane loading here, in-plane loading here, in-plane loading here, then what happens? The distribution of stress, we can have stress in this direction, we can have stress in this direction, but across the thickness of the plate, across the thickness of this paper, we can say that this stress is so small that we can neglect it. This is so small as compared to the other stress field. So, this is a problem of plane stress problem. So, what are the stress components we have here? We have that we have sigma, in this we have sigma x, then we have sigma y, and then we have a shear stress on this plane, sigma x y. So, for a plane stress problem, we have 3 components of stresses, sigma x, sigma y and sigma x y. Similarly, these are the strain epsilon x, epsilon y and epsilon or gamma x y, and this is how the stress and strain are related to each other for plane strain problem. So, essentially, if you recall, the entire thing, this is your D for plane stress problem. Similarly, for plane strain problem, the strain in a particular direction is 0. For instance, if we talk about a dam, very long retaining wall or a dam, one dimension is so long that along this direction the strain can be neglected. So, the strain is confined within a plane. So, this is called plane strain problem. So, in that case, so strain in a particular direction is 0. So, we are left with only 3 strain components, epsilon x, epsilon y and the shear strain on that plane gamma x y, and these strains are related to stresses, corresponding stresses like this. So, again this is essentially the D for plane strain problem. So, already we know what is D, and we know that stiffness matrix K is equal to integration B transpose D and then B and then d omega, right. This is the stiffness matrix. So, in this stiffness matrix already we have D for 2-dimensional problem. Now, what we are going to do now is we take an element and then we will see what is the expression for B. Now let us do that exercise. So, this is the triangular element. Now, what are the degrees of freedom we have? Now, at every point we have 2 degrees of freedom, translation in x direction and translation in y direction. Okay. So, suppose this node is, let us give some node number 1, this is node number 1, then this is node number 2, and this is node number 2, and say this is node number 3. Okay. Now, what are the degrees of freedom we have? Suppose degrees of freedom we have, this is u1 and this is v1. So, u in x direction, v is in y direction. Similarly, at node number 2 we have u2, and then along y direction we have v2, and similarly here we have u3 and we have v3. Okay, we have v3 here. V3. So, total 6 degrees of freedom we have. Now, if you recall, what was our first step? First step was to see these values are u1, u2, u3, v1, v2, v3. These values are the values of displacements at the nodal points, right? Now, what we did, we need to find out the values. If we have to find out values at the intermediate point within an element, then how to do that? In order to do that, we need a functional representation of this entire displacement field, right? So, in the case of truss or in the case of beam, in the case of truss, we assume that your u is equal to ax plus b in a linear function. Then in the case of beam, we assume it is a cubic function. Similarly, here also you have to start with an assumption. Now, what form you take, whether it is a linear, quadratic, cubic, what form you take, that depends on what are the information you have and whether those information sufficient to find out the constant associated with that approximation. Okay. Now, what are the information we have? We know, say here you see u and v are two independent displacement field. Okay. So, here we have to approximate u separately and we have to approximate v separately. Unlike in the beam case, where we approximated only the v and the derivative of the v, dv dx gave us slope. It is not like that. Here u and v are both different independent degrees of freedom, and they have to be represented separately. Okay. So, essentially for a given degrees of freedom, say for instance u, we have only 3 information. So, 3 information means 3 values at the 3 nodes. Similarly, for v we have 3 information, 3 values at the 3 nodes. So, what we take is we assume a polynomial which has 3 constant, okay, which has only 3 constant. Okay. So, let us assume u is equal to, say u is equal to at any point x and y, that is equal to say a plus bx plus, since it is in 2 dimensional, we should have a function of y as well, it is cy. Okay. Now, some of the important point we will discuss at the last class. One point, of course, as I was mentioning how to calculate the error between the prediction and the actual thing. This is one point, and another important point is this one, that suppose instead of a plus bx plus cy, if I take a plus bx plus c x square, it is not a function of x. Or instead of that, if I take a plus bx square plus cy square, this is also an approximation which has 3 constants. So, there are many possibilities as of now, because we do not know what are the conditions need to be satisfied while choosing a particular polynomial. That condition also we will discuss at the last class of this course. Okay. Now, so this is u. So, now what information we have, that u1, so x is equal to x1, this is, suppose coordinate of this is x1 y1 and this is x2 y2, and similarly here it is x3 and y3, right. Now, then what information we have? We have that at x is equal to, at x1 y1 u is equal to u1, x1 x2 y2 u is equal to u2, x3 y3 u is equal to u3. Let us put that expression. So, u1 is equal to a plus b x1 plus c y1, and u2 is equal to a plus b x2 plus c y2, and u3 is equal to a plus b x3 plus c y3. Similarly, we can do it for v. Let us not do it because it will be the similar exercise. Now, from this expression, from this entire expression, what we can write is, from this expression what we can have is we can have that the constants a, b, c, constant a, b, c is essentially, or we can write it like this, u 1 or a, no, not that, that is, yes, okay. So, we can have a matrix which is 1 x 1 y 1, then 1 x 2 y 2, 1 x 2 y 2, and then finally finally 1 x 3 y 3, that is into a b c is equal to u 1, u 2 and u 3. Okay. Now, so if we solve this, we know what is, if we solve this equation, then we can get a b c as a function of x 1 as a function of nodal coordinate and the nodal displacements. Okay. Now, once we calculate this a b c and substitute that a b c in this expression, in equation number 1, say equation number 1, then what will happen? We get an expression, you please do that exercise, we get an expression as u x y, that is equal to your n 1 x 1, the same thing we have n 1 x 1, n 1 which is a function of x and y both, u 1 plus n 2 function of x y both, u 2 plus n 3 function of x y and u 3. Okay. And what will be n 1? What is the expression for n 1? The expression for n 1 will be, I just give you the final expression for n 1, n I will be 1 by 2 delta. What is delta? I will tell you. Then alpha I plus beta I x plus gamma I y, where delta is equal to the area of this triangle. Okay. Now, what is the area of this triangle? If you recall, the area of this triangle will be half of the determinant of this, determinant of 1 x 1 y 1, 1 x 2 y 2 and 1 x 3 y 3. So, determinant of this essentially gives you delta. So, this is delta, and what is alpha 1, alpha 2, alpha 3? Then alpha 1 is equal to, this gives you that your this is alpha 1 is equal to say alpha is equal to your x 2 y 3 minus x 3 y 2, and then beta is equal to y 2 minus y 3, and gamma is equal to x 3 minus x 2. Okay. So, this is the information we have, okay, or it is alpha I you can put. Okay. Essentially, for all I, this is same. Okay. So, this is alpha, beta, gamma, and this is your final expression of n. Okay. Now, so let us, if you recall the shape functions, you can do this exercise please. If you recall, there are certain properties that shape function must satisfy. The one property was the shape function satisfy the Kronecker delta property. Kronecker delta property means that the shape function, suppose if you are talking about n 1, then n 1 is 1 at the first node, node number 1, but all other node these values are 0. Similarly, if you take n 2, then n 2 will be 1 as node number 2, but all other nodes these values will be 0. So, that is the Kronecker delta property. Let us see whether this is being satisfied or not. So, you can take for instance n 1 for n 1. Suppose n 1, if I calculate n 1, so n 1 will be 1 by 2 delta, and if I do it for if I do it for this is x 2 minus y 3, x 2 y 3 minus x 3 y 2, and then plus beta is y 2 minus y 3, y 2 minus y 3, and if it is if I am calculating at node 1, then this x will be x1 and then plus gamma is x3 minus x2 and again this will be y1. So, if I do that, then you will see that this is essentially the determinant of this. So, this becomes 1. Okay. Now, if I do the same exercise, if I calculate same n1, let us do it here, n1, but node number 2. If I do that, this becomes 1 by 2 delta, then x2 y3 minus x3 y2, then plus y2 minus y3, this become x2 and then plus x3 minus x2 and this becomes y2, and then please check what is this. Okay. So, these values will be that x2 y2, these x2 y2 and these x2 y2 will get cancelled. y3 x2 and y3 x2 will get cancelled, x3 y2 and x3 y2, this will also get cancelled, this will be 0. So, n1 at node number 1 is 1, n1 at node number 2 is 0. Similarly, you can have n1 at node number 3 will also be 0. So, similar thing you can do to check whether this satisfy this Kronecker delta property or not. And then if I have to draw the safe function, the safe function will be, suppose if I draw it, if it is node number 1, node number 2 and node number 3, then for node number 1 the safe function will be, this is something like this. This will be the safe function. So, this is 1 and this is 0, this is 0. Okay. Try to visualize it in a 3-dimensional space. Okay. Similarly, if I have to draw, if I draw node same figure, if I draw for node number, it is node number 1, 2, 3, 1, 2 and then 3. If I draw safe function for node number 2, this will be this and this. Okay. So, this will be the safe function. This will be the safe function. And similarly, if I draw it for node number other node, so this is node number 1, 2 and 3, for this node, this will be, it is 1, this is 0 and this will be 0. So, this will be, this is the safe function, this is 1. Okay. So, it will be linear because our approximation was linear, this approximation was linear, this is a linear function. Okay. But for instance, if your node is, we will not discuss that, just to for the completeness of the discussion I am talking about. Suppose if you are using a 6 noded element. So, we have a node here, we have a node at 3 corners, and similarly we have a node at the sides. So, in that case what will happen, how many unknowns you have, 1, 2, 3, 4, 5, 6. So, you can have an expression, for instance like this, where u is equal to u x y is equal to a constant plus b x plus c y plus say d x square plus e x y plus f y square. So, a, b, c, d, f are 6 unknown, you have the values at the 6 nodes, you can get these corresponding safe functions. In that case, your safe function will not be linear, in that case your safe function will be quadratic, but still they satisfy that property at that particular node, your safe function will be 1 and rest other nodes it will be 0, they satisfy that property. Okay. So, now once we have calculated the safe function, we are almost done. So, similarly we can, so u is equal to now can be written as u at x y can be written as n I u y. N I u y means summation over I n1 u1, n2 u2 and n3 u3. Similarly, v can be written as is equal to the same safe function we can use for v as well. So, this is how the displacement is approximated. Now, once you approximate the displacement, then how we can write the displacement vector, if you look. So, displacement vector can be written as, so once you have this, we have to calculate the strain can be obtained as, suppose if I have to find out del u del x is the epsilon x. So, epsilon x can be obtained as del n I del x u into I. Okay. Similarly, del v del x can be obtained as del n I del V del y into V I, and then shear strain, suppose del V del x plus del u del y, they can be obtained as del n I del y del n I del y del n I del x into V I plus del n I del y into u y, and so on. So, we have, so this gives us strain displacement relation. You see. So, once you have the strain displacement relation, means from this expression we get what is the expression for B. From this relation we get the expression for B. Once we get the expression for B, then we have to substitute that B in this B transpose dB and integrate it over d omega. Now, in the case of beam, we could integrate it in a closed form, but many times it may not be possible to integrate it, because now it has to be integrated over the entire over a triangle, right. So, it depends on what is the size, what is the shape of the triangle. So, in many cases it may not be possible to integrate them in a closed form. In that case, we have to do integration in a integration numerically. Okay. So, you might have done a course on numerical methods, and you studied there are many techniques for many numerical methods for integration. Okay. Again, just name of the methods we will discuss at the last day of this week. Okay. So, this is how you can calculate B and the corresponding stiffness matrix. As far as the load vector is concerned, again it is the same way you can calculate the load vector. Okay. Now, quickly, as I was mentioning, quickly, just if I give you the if I take you this another element, this 4 noded quadrilateral element, and give you how to construct the shape functions of this element. So, this will be again quickly take you have a you define x and y coordinate, x y coordinate, and then we have a 4 noded quadrilateral. Suppose this, and these are 4 nodes, these are the 4 nodes, and then 4 nodes are named as, suppose this is node number 1, node number 2, node number 3 and node number 4. And suppose suppose this is your local x coordinate, this is your x and this is your y direction. Okay. Small y and this is small x. Okay. So, node number 1 with respect to small x small y, node number 1 coordinate is 0, and suppose this length is L, this length is L and this length is h. Okay. So, node number 2 coordinate will be L and 0, node number 3 coordinate will be L and h, and so on. Okay. So, now at every node we have 2 degrees of freedom, here also 2 degrees of freedom, u1 and then v1, and then similarly u2, v2 and u3, v3, u4 and then v4, right, v4. Now, so if the first step is to have an expression for u and v, the field variables. Here the expression will be, it is a 2 dimension. So, expression will be say a plus bx plus cy plus, this is very important. The last term, for the time being, you take it for granted. As I said, how many terms and what are the terms to be considered in that expression, we will discuss in the subsequent week, but for the time being, you take the last term for granted. So, d into x y. Okay. It could be say d into x square, it could be d into y square, but particularly we have taken d into x y. We will discuss that y. So, this is u. So, what are the information we have? We have the nodal values at the 4 nodes. So, u1 will be a plus. Now, let us now you see the expression is written in terms of the local coordinates small x and small y. So, at node number 1, so essentially x1 y1 the coordinate will be 0. So, u1 will be, if you substitute 0, u1 will be 1, u1 will be a. Okay. So, and then similarly, then u2 will be here x is equal to L, y is equal to 0. So, it will be a plus b into L and y is equal to 0, and u3 will be, it will be a plus b into L plus C into H plus D into L into H, and finally U4 will be X will be 0 and Y will be H. So, A plus C into H. So, this part is 0. So, these are four equations we have. Now, we have to find out these four equations. We have to find out these constants A, B, C, D, four constants, and then substitute that constant in this expression. And if you do that, then we get finally x y is equal to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Okay. Similarly, we can have a similar expression for v. And what are the expression for n? The expression for n is, I will just write the expression for n. N1 will be 1 minus x by L minus y by h plus xy by L into h, and then n2 will be x by L. Please verify these values, xy by L h, and n3 is xy by L h, and finally n4 will be y by h minus xy by L into h. So, these are the values of this. Okay. Now, you can quickly verify what is n1. N1, suppose say n1 at node 1 is equal to x is equal to 0, y is equal to 0, this is become 1. N1 at node 2 is x is equal to L, y is equal to 0. If I substitute x is equal to L and y is equal to 0, it is 1 minus 1, this becomes 0. Similarly, N1 at node 3 become, it is x is equal to L, y is equal to h, x is equal to L and y is equal to x is equal to L and y is equal to h. If you substitute, this is also becomes 0. And finally, N1 at node 4, this is also becomes 0. So, similarly, you can see that these satisfy the Kronecker delta property. Now, not only that, there is another property called partition of unity property. At any intermediate point, if you sum all the shape functions, these shape functions will be 1. So, you sum them, all these shape functions at any point, okay, you will see this will be 1. So, let us do this exercise. If we take summation of ni, so you sum them at any arbitrary point, if you sum them, then what will happen? So, this XL will get cancelled, this will get cancelled, this will get cancelled and this will get cancelled. So, sum of all the ni is equal to 1 always. Okay. So, by construction itself, it is, you do not have to do that exercise, here itself it is 1. Okay. So, this is a partition of unity property, that is an important property. Now, quickly, so once we have n, the next is we have to calculate the strain. Strain is a function of, we can differentiate this expression with respect to the coordinate axis, we get the corresponding strains, and once we have the strain, we get the strain displacement relation, that is B. So, once we have B, D is already discussed, what is the expression for D for plane stress and plane strain problem. So, once we have B, substitute that in the expression, we get the stiffness matrix for a 4-noded quadrilateral element. Now, quickly, if I have to quickly let us see the what is the shape of this of the shape functions, and these are the shape of the shape function. Okay. So, these are the, so this is 1 and all the places it is 0. So, your shape function is essentially this, and shape function is linear, not linear, it is actually bilinear. Okay, linear in x and linear in y both. So, it is bilinear. So, again it is for n3. So, this is for n1, this is for n2, this is for n3 and finally, this is for n4. Okay. So, this is the shape function and this is the shape function, just a plane. Okay. And finally, your this will be the shape function. What is that? Yes. Yes. So, this will be the all are 0. So, this will be the step function. Okay. This will be the step function. So, this is how we can now, if we have a 6 noded, if we want to have this kind of element, suppose element of this kind. If we want to have an element of this kind, say 8 noded element, the same exercise you have to do. We have to start with an approximation of u and then find out and substitute the boundary conditions at every point and get an expression for n. Once we get n, we can calculate the stiffness matrix subsequently. Okay. Next class what we discuss is, next class really will again similar to 1D problem, beam problem, we translate the 2D beam element to the formulation into a code and solve one 2D problem, and then through that solution we will try to understand some more important aspects of finite element method. So, I stop here today. See you in the next class. Thank you.